So I'll kick this off. I'll be very light on the business side, and I'll give you a bit of an overview, and then the bulk of this presentation will be Ori. So I'll share, and then Ori, you can share. You should be able to see my screen. Let me see. Right. Okay. So and I'll let Ori introduce himself if he wants to a bit deeper. But I'll run through the outline. So first of all, introduce you to Augury, kind of company and solution, and then Ori will dive into how it actually works, and then present out of all the different technical challenges of bringing machine health to market and actually building out a solution that utilizes the full spectrum of AI capabilities plus hardware plus sensing. Plus solving some real life use case and challenges. He'll dive into a couple of them, right, and go quite deep there on the technical side. So Augury today is a high growth scale up company. We have a tremendous data set for our industry, machine health within industrial environments, primarily rotating equipment. And we have a good number of large Fortune 500, 1,000 manufacturers as our customers. And one of the only companies in the space with this level of growth, and that has actually been able to scale from, let's say, a pilot to consistently multiple, dozens of factories across the world, becoming a natural part of the manufacturing environment, and actually integrating the solution that utilizes AI very heavily into the day-to-day work of frontline workers in manufacturing. So that's where we are. Mission driven. So our vision is to build a world where people can always rely on the machines that matter. A combination of AI and technologies around it, and sensing and IoT, but to really create a layer that can actively analyze, diagnose, and provide value on any machine. But we're starting with machines that matter in industrial manufacturing and primarily in continuous process manufacturing, fast moving goods, a lot of rotating equipment. And then can we analyze, diagnose that automatically so that those machines are essentially reliable significantly more than they are today. And we provide that as a service. So our solution is full stack. So we combine sensing, hardware, connectivity, AI, algorithms, and then prescriptive diagnostics that translate into actual outcomes. So not just here's what the thing is, or here's what the insight is, but you have to actually act upon it, and then the activity gets translated back into that learning and kind of driving continuous value for the customers. And we do that as a service, meaning everything is on a subscription model. We don't sell parts of this separately. They just pay us an annual fee, and they get outcomes day to day. And we also have a way of guaranteeing. So the maturity of the diagnostics is today high enough so that we actually guarantee it, meaning that if Augury is installed on a machine and that machine fails on Augury's watch, we pay to repair or replace that machine. And so that speaks to the accuracy and confidence of the algorithms. And customers tell us that it's like having an army of experts looking at every part of every machine, 24/7, and that's obviously well beyond human capacity. So there's a flywheel effect to how we work, right? It's a tremendous data set, again, for what we have of actual live issues with machines, and millions of machine hours that are monitored, that have enabled us to create, get the algorithms to a level of maturity that we're detecting a very, very high level of performance and of these issues, and a very high level of specificity in terms of here's what exactly the issue is, that in turn allows the customers to trust the platform, and we enjoy very high engagement. So if Augury says there's an issue and here's what the issue is, then there's a 90% chance that the person will go and make the repair or the adjustment based on that alert. And that in turn translates to very quick payback and ROI and time to value for our customers. So we're very quick time to value. And then we also create a foundational layer for other means of digitizing. So that the ability to drive those insights and get those insights helps customers do then derivative work that I can talk about it in just a minute in terms of optimizing their overall operation, not just machine health and predictive maintenance. And
but before you go on, can I ask a question? I guess maybe.
Yeah, go ahead.
Yeah, and spurred a little by Erez there, who's doing a little bit of agitating for us to be asking some questions. One question, I was fascinated by that guarantee that you made. Yeah. Is that on prediction ahead of time, or is that on detecting or not? Whether I see your 99% detection, and I'm curious about the detection versus prediction of failure.
Sure. Typically, the prediction, most of the issues on these types of equipment are slow developing. So our prediction is typically months ahead of time.
Okay.
But what we're guaranteeing here is that if a machine fails on our watch, if we say that it's fine and it's not fine, then we trigger the guarantee, right? And now we're moving into the next level, which now we're guaranteeing the performance of that operating line. So the business outcome, not just the detection of the issue. Now that becomes a little bit more complicated, but now we're getting to a level we can start doing that. Okay.
Got it.
Sure.
Thanks.
Absolutely. And then the other part of it is the approach. So we kind of set the standards. So it's monitoring, diagnostics, guidance, planning, and activity, and we're setting standards across all of these, and they have to work together essentially as a continuous, virtuous cycle of integrating AI and having AI become a symbiotic part of how manufacturing works and how maintenance and reliability works. So monitoring means it needs to be ubiquitous at the highest possible quality that serves the needs of diagnostics. Diagnostics need to be fully prescriptive and not just here's what might happen, but exactly what's going to happen. Guidance, it's not just enough to drop the diagnostics over the fence, but the people who are planning the activity and scheduling the maintenance and scheduling operations need to then themselves start working in a predictive sense and only doing the right activity at the right time, essentially eliminating downtime and increasing their capacity. And then we believe that production workers have a tremendous amount of knowledge that is marginalized today, and essentially we need to benefit from the collective intelligence. That means giving them a lot of autonomy to make data-driven decisions, insight-driven decisions, but also then capturing their knowledge. So we have a collaboration platform, kind of like a Slack or Microsoft Teams for machines, where operators are not just acting on Augury's insights, but they're actually making some judgments and decisions that are captured in the platform. And then we can use that to improve the overall life cycle of that machine or that production. So that's a virtuous cycle. That's how we approach it. And you see our sensors on these machines. And so when we talk about prescriptive, we can see here the full history of that machine, and over that history, the machine has been automatically diagnosed that deterioration, another deterioration, then was repaired, and that repair is automatically diagnosed. So there's an improvement in the health of that machine. So that full life cycle is captured. But the prescriptive diagnostics, what we mean is that here's a specific issue and specific component of this machine, radial imbalance in the motor. Here are the root causes, and here are the actions that need to be taken in order to eliminate that issue. There's prescriptive analytics, and here you also have an estimated, what's the severity and when is that issue going to happen. So that's more or less the kind of prescriptive approach. And behind the scenes, there's a full visualization of the rationale of why the algorithms kind of on a time series are detecting the issues, and you can dive into that data, and you also build derivative work on top of that data. You can see here installation sensors in the wild protecting critical equipment. In this case, this is a Colgate toothpaste manufacturing line. And now we're starting to move from just detecting issues in the machines to actually understanding how the health of that equipment is actually status correlating to the recipe, the formulation, the outputs, the throughput, the yield, the quality of that whole production line. And it becomes a foundational layer of insight, not just data, that can help us move towards dynamic production, right? Should I produce this formulation in this facility or this facility? And that's based on our inputs and the actual state and health of those machines. And then you can actually start simulating what would happen in the future. So I'm not going to go too much into that, but that's kind of the next levels of where we're going is beyond just reliability. We're going into dynamic production. production.
Artyom,
we
one
work
question
with,
we just
yeah.
had from the audience is how do you deal with kind of firm-to-firm security concerns? Like, is it all online? Do you just push it to your own cloud, or is
Everything's,
it all...
yeah, our solution is entirely in the cloud, and we have robust security.
And it's all public cloud or enterprise private cloud?
It's everything today is public cloud. And if you look at the logos of the companies here, some of them are very competitive between each other. And so while it was a concern a few years ago in the CPG space, it's still a concern in the chemicals and petrochemical industries. We have been able to a little bit break through that and help customers understand that the public cloud in this instance is as secure and probably more secure than the private instances. And so, you know, but obviously we have really robust security and standards and so forth. And also we take in diagnostic data, not operational data, which makes it a bit easier, right? It's not the data, we don't control the machine, we just diagnose it externally, non-intrusively.
Sorry to interrupt, but another question would be either you or Ori, maybe can you address a little bit more specifically how you're collecting your data and what kind of data you're collecting?
We'll do that I'll run through this, right? Because Ori has a whole component.
Okay, that's fine.
All the technical stuff or questions, you know, that will be there.
Yeah, okay.
Ori's. The other thing that we're doing is that we're not just retrofitting machines and helping these manufacturing customers, we're actually embedding the technology into the machines themselves. So we have partnerships with companies like Grundfos, which is the world's largest pump manufacturer. You know, the idea is and the goal is for the machines to diagnose themselves in the future, right? So not just sensors or machines, but the machines becoming smart and diagnosing themselves. So that's what we're doing with them. And the impact is essentially zero unplanned mechanical downtime for this equipment. And then what do you do next on top of that? So, you know, we typically see something like this where 30–40% of equipment across any production facility on kind of statistically has about, you know, some level of issues that customers don't know about. So when we're deployed, immediately they know the issues that they have and they go and fix them. And eventually they get to the right side of this chart where there's virtually no unexpected issues happening with their equipment. And the impact on the operation is tremendous. Reduction of costs, increased production capacity, increased life cycle of equipment, and then starting to take that as an input into dynamic and agile production, right? So we're turning the machines into sensors themselves for the whole production line. I think this is probably my last slide is, you know, this is not kind of pilot stage. We're rolled out with some pretty large customers and providing value every day. There are some customers where we save a machine every day for them. In some cases like Frito-Lay here, you know, a year of deployment is zero breakdowns, zero interruptions, zero incremental costs, and unlocking capacity. So if you think about a manufacturing customer, if we can unlock 4 months of production capacity and we can move that to 10 months, 12 months, then they can avoid building a new facility. So now we're it's a non-incremental improvement in terms of production capacity for manufacturers, and that's where the value is. So let me stop here. Hopefully this provided some context for you guys on the business side.
Yeah, that's great. And actually, Artem, I'd like to follow up with you offline and get a little bit more data on some of these case studies. I've got a big study I'm publishing, and you know, I'm looking. Predictive maintenance was actually kind of the #1 use case, and so I'd like to have a few case studies that we can put numbers to publicly. A lot of the people that have responded to our study, no surprise, don't want to put public numbers out there. So to the extent you already have approval on some of these, I'd like to talk to you. So Eros, if you can connect us, that'd be super.
I think these are all public, or most of them public, provided, you know, we have a good number. So yeah, thanks, and let me kick this to Ori.
I think we have one question in the crowd, but you know, people could just unmute and ask.
Okay, shall do. Thanks for the overview. So this is very similar to my thesis, which is about predictive maintenance and interventions to improve operations. And a challenge I faced is that there are a lot of nuances when you go about doing that. Like things fail in different ways, and considering your business model is servicing different business and different machines, like how do you go about tackling that complexity? Do you there's must be a lot of human in the loop at first, and how is that scalable as you go broader and broader?
So over the last 9 years, we actually solved well for rotating equipment, right? Rotating equipment that and different versions of pumps, motors, compressors, chillers, and so forth. We have actually already have pre-built models that are highly functional, highly accurate, and that are very well replicable from machine type to machine type within that realm. And then Ori will talk about how we then take, don't start from the scratch, but start from the middle with transfer learnings and other methodologies in order to go, if we want to include a new piece of equipment, it's actually a pretty quick ramp up for us at this point. We don't start from scratch. So yeah, I'll let Ori dive into that.
Hi guys, can you hear me well?
Yes.
Great. So a little bit about myself. My name is Ori, as you already know. I'm working at Augury for more than 5 years, mainly around sensing development and algorithms. Started as an algorithm researcher, then I was the principal scientist in Augury, and in the last year and a half, I'm heading the algo, data science, and physics teams in Augury. Prior to Augury, I was a researcher, did my PhD in the Technion, my master and PhD, also around noise analysis, but different noise, a quantum noise of electron pairs in superconductive materials. A bit different, but at the end of the day, noise is noise and the analysis is very similar. Okay, so as Artem said, we are trying to prevent unplanned downtime. This is where the main pain points of our customer, and we are trying to do our best to help them avoid it and prepare in advance to do repair and maintenance. And usually machine, when they start to fail, when they start to show some signs of degradation in their performance, we see signs in the ultrasonic spectrum, the magnetic spectrum, and vibration. Ultrasonic, it's when there is small friction between, for example, bearing balls, which start at really high frequency. It can be even 2 years before the actual failure of the bearing, but these frequencies start to show some signs of ultrasonic emission. Also, an electrical example is transient current in induction motors, starting with a real small portion of transient current until it later on convert to short that destroy the motor. For this, we built our system based on vibration and magnetic analysis. We have low noise, high band, high resolution MEMS accelerometers. A couple of years ago, MEMS accelerometers was not that popular in the vibration analysis industry because they didn't have the accuracy as piezoelectric one, but in recent years, they reached to high level of performance. And in order to have a wireless solution, wireless sensing unit, you cannot use a piezoelectric component, you need to use MEMS sensor, but today they achieve really high accuracy. We are also oversampling the MEMS in order to reach to ultrasonic frequency, which gives high value to measure the ultrasonic energy. In addition to the vibration sensor, we also have a magnetic sensor, as I said before, to analyze electrical fault, magnetic signature of electrical faults. But in addition to that, which is really important, we also use the magnetic sensor in order to detect operational mode, which is very, very beneficial and crucial in order to differentiate between machine health anomalies and operational anomalies. Since in terms of signal, operational modes is also an anomaly in the signal. Even an on-off of the machine is an anomaly in a signal, but we need to differentiate between these types of anomalies and true machine health anomalies. And we do that using the magnetic sensor and fusing the magnetic and the vibration sensor. Along with that, we also have a temperature sensor, semiconductor thermistor to measure the surface temperature. And in addition to that, we use a specific edge sampling technology for sensor fusion to sample the magnetic and the vibration sensor within each sensing unit synchronously in an accuracy of microsecond in order to correlate between the phase of the vibration and the magnetic. Now, the overall AI flow for a single machine, for example, so a single machine is usually composed from some driving motor and driven equipment like a pump, fan, chiller, and so on. And usually we have 4 sensing units on a machine, 2 on the motor and 2 on the driven equipment, mainly to be as close as possible to the bearings. In each sensing unit, we have, as I said before, 3 vibration sensor, 1 magnetic sensor. And at the end, it turns out with the sampling frequency that we have and the sampling configuration that we send to the cloud for each machine 1.3 million points per hour. Now, the data is being sent to the cloud, and then we apply a validity algorithm first to make sure that the data is valid for diagnostics, that there is no hardware issue or environmental issue. Then we apply a signal processing algorithm, converting the voltage data from the sensor to real physical quantities like acceleration, then doing numerical integration to velocity, displacement, magnetic fields, and then starting to calculate the relevant transformation for diagnostic, the spectrum, Hilbert transform, and the capstone. And then after we have all the, let's say, the vectors of the transformation and the waveform, we are starting to calculate the features. Now, the main technology of feature extraction that we use today is based on domain knowledge. We also on signal processing knowledge. We are calculating the features using DSP techniques in order to calculate quantities that are related to machine health and related to the operational mode of the machine. For example, a feature, we have energy feature like the RMS of the signal or RMS per bins. We have also a signal feature like the moments of the probability density function. For example, the skewness is highly correlated with mechanical looseness faults due to the gravity force. Kurtosis is also correlated with bearing wear due to the high noise that it generates. So we have fault feature, signal feature, a lot of feature that translate roughly to 1,000 feature per machine per hour. Then we send those feature to another pipeline that perform time series analysis on those feature, look on the time dependency of the feature, statistical feature based on the time series of the feature, starting to fuse between the sensor to get operational index. And when we have it all, the time dependent feature and the snapshot feature, we send that to our detection system. And our detection system is composed of 2 layers. One is the anomaly detection and the second is the fault detection. The anomaly detection is designed for high recall because, as you explained from our presentation, we cannot allow to miss any fault, any type of machine health issue. We are guaranteed to deliver that. But in addition to that, we need to also provide the specific issue and the specific severity of the issue. And for this, we have the fault detectors. And the fault detectors are designed for...
Wait, can I actually ask
Yes.
a question? Because I again, like Jerry, worked on something related to this during an internship. So in the company I worked in, and they were not doing circular motors, you know, it was a company that cuts fabric of sorts. One of the issues I found is their own errors are not well classified, right? Like the company has, you know, their engineers invented some risks and faults. It's not necessarily as well classified as one might think or standardized. So when you're working and embedding this at customers, it's 2 questions. One, it sounds like you only focus on like a rotating pump type of machine, and maybe I misunderstood that. And 2, what do you do when the customer says, well, you know, we have different errors, we call them different things, we don't have a name for this? Like, how are you able to really transfer that knowledge?
So it's a good question, and I will start with the first one. is that, yeah, a solution today is designed for rotational machine. Those are motors and pumps, fan, chiller, compressor, and so on, which are based on similar components, I would say. There are differences, of course, between the mechanics of the machine, but the main essential components are similar, and therefore the signature is a bit similar, and I will explain later on how we combine all the data set in order to enjoy most of the data and still differentiate between type of machine. So we are not applying our solution to a machine that we don't have knowledge or machine that we didn't train our models on. This is one. Now, regarding the next question, if I understand that correctly, so at the end of the day, we have the fault model, which are prescriptive model for specific fault that we have. Usually, or from what I know, machine have somewhere around 40 types of fault, where you can list the 10 main type that they are around 95% of the fault. So we have an automated model for those 95% of the fault, and the rest are covered by the anomaly detection algorithm. Now, in addition to that, if there is any issue that we didn't see before, but there is an issue that manifests in the sensor data, we will be able to catch it with the anomaly detection algorithm, because the anomaly detection, you can think of it as like per machine model. Each model or each machine has its own signature and its own baseline, which is a running baseline, and the anomaly detection always compare the machine signature relative to its baseline. So if there will be any change in the machine, in the sensor data, we will be able to catch it. This is true that we might not know to provide the specific fault that led to it, but till now, we haven't seen such an issue.
Okay, thank you.
Sure. So, and I will go a little bit deeper later on discussing the algorithm. So just to close the flow, so the anomaly and the fault detection generate confidence levels. 99.87% are closed automatically by the algorithm, while 0.13% are being sent to our detection system, where if the confidence of the algorithm is high, we send it directly to the customer, alerting it via SMS, email, and if the confidence is low, we send it also to our vibration analyst. And the vibration analysts, which are expert in vibration analysis, category 4, they are used for two main reasons. One, to help to improve the accuracy of the algorithm and help us labeling the data and increase the supervised data. But in addition to that, they are also serve as a layer of explainability to the customer. And this is very important, because sometimes the customer don't want to interact with an algorithm. He wants to interact with a human that will explain to him, will show him the signature in the data, and will guide him what to do. Any question?
Yeah, I'm curious, how often is this analyst queried, and like how many analysts do you have employed, and how scalable is this analyst basically?
So actually, I have a good slide for that, which I haven't prepared in advance, but the main goal is that the algorithm accuracy will evolve much faster than the number of machine, or let's say it will be like a log curve. And this is what happened in the last like 6 years that we are developing the algorithm. So yes, we need a vibration analysis in order to give a full prescriptive diagnostics. And also, as we learned, and I can give you even an example, I hope it will translate good. If you go to a doctor and the doctor order a blood test, and you know that the algorithm will analyze your blood test. So if the blood test result from the algorithm will say that you have some flu, you have something virus, you need to rest a couple of days, for sure you will agree with that and just go and rest. But if the algorithm will declare that you have some severe issue or something else, you probably want to talk with a doctor, right? And even a couple of more doctors to get a second opinion. Now, this is the same with our customers. At the end of the day, when you tell them that everything is good, they believe the algorithm. But if it's a severe issue where they now need to shut down the line and replace something which is really expensive, they will want to talk with an analyst.
Mm-hmm.
So this is one of the reasons, or one of another reason that we have an analyst. Now, at least now we scaled very fast, and we didn't see an issue with the number of analysts or the scalable issue. And it seems, at least for now, that we are ready to increase our machine, let's say, coverage in an order of magnitude without any problem with our current analyst that we have.
Makes sense. So I'm curious, like, if for a typical customer, how often will an analyst talk to a typical customer?
Well, it depends. I would say, first of all, they interact with our system. They are not talking on the phone or something like that. It really depends, and I don't have the number with me, but I would say that let's assume an industrial facility with, let's say, 100 machine.
Mm-hmm.
It can happen that this customer will get one anomaly per day, so it might get an interaction of a couple of interactions per week. Artem, those numbers sounds reasonable to you?
Yeah, and the goal is, so just to give you, let's say, no augury, and let's say you have analysts, let's say you're able to collect data. One analyst is able to, in a fully manual environment, one analyst is probably able to analyze and cover a few dozen machines a day if they work full time. Our analysts are able to cover 10,000 of machines a day. They work full time, and the curve of how much they're covering is really growing exponentially. So we will probably within 2 years get to an analyst covering a couple 100,000 of machines automatically. And then what Ori mentioned around interactions, well, it's support. It's not diagnostics, right?
Yeah.
So basically that's where we are.
Mm-hmm. Thanks.
All right.
Can you talk a little bit about the difference in the algorithms you're using between the fault detection and the anomaly detection in the last slide?
I'm planning to get to it, but
okay, all right. I can hold the question until you get to your section.
General, I will just say in general that the types of algorithm that we use for the anomaly detection are time series analysis algorithm, which try to detect specific anomalies, and they are semi-supervised, while the fault detection algorithm are classifier, which are trained in a supervised manner, fully supervised.
Okay.
Now, as you see here, and as I said before, the anomaly detection is designed for high recall. There is a cost for high recall, as you know, which is the cost of precision. The fault detectors are designed for high precision, meaning that if we are not sure what is the specific fault, we can send the anomaly to the customer to give it, and we only send it automatically to the customer when the precision is really high. Our database, the data that we use today for training the algorithm, is based on 80,000 unique machine in our database with over 50 million hours of recording, which is quite a lot, even in terms of a supervised data set. Here you can see an example of how the anomaly and faults are working in Unison. Oh, by the way, something that I didn't say, which is very important, we are not hiding any algorithm results from the customer, even the low confidence ones. Everything is displayed, the alerts and the confidence level of the algorithm is displayed continuously in our web platform. Here you can see an example of the bearing wear confidence level. Bearing wear is a type of fault in machine and mechanical looseness. And you can see how the cliff anomaly detector and the trend anomaly detector, which are different type of anomaly patterns, how they trigger an alert and how the confidence level of the relative fault increases with respect to the anomaly detection. So they work in Unison really good. Not all the pattern, as you can imagine, look great like this, but most of it are like this. And again, we are not hiding any alert or any confidence data from our customers. Now, what I wanted to share with you today is not only how our algorithm was great and how everything is perfect and solved, because as you probably know, working on algorithm and working in this industry, there are many challenges in order to reach a high accuracy algorithm, and those are, you can list it between hardware related challenges and data related challenges. In terms of the hardware related challenges, one challenge which is really bothering us is let's say the trade-off between hardware quality and power performance. For example, we want to sample the sensor as long as we can, as much as we can, not only once per hour for 4 seconds, for example, but let's say once per every 5 minutes for 10 seconds to increase the frequency resolution, but that will cost in a battery power. And today our battery lasts for 3 years, but once we start to play with that, we can decrease it very significantly. So we have some trade-off between that. Another very challenging issue that we face, and I will talk about it and elaborate in the next slide, is the modeling from multiple hardware sensor. This is different. This is different when from, let's say, the computer vision world, where you can use a classifier or build a classifier that was based on data collected from multiple cameras, as long as the cameras are in some standards, while in vibration sensor, in accelerometers, you cannot do that due to the acoustic response difference between sensor, and I will elaborate on that a bit more. Touching a bit on data-related challenges, so multiple expert labeling is a real challenge, like multiple doctors that have a different opinion when they look on an MRI. So similarly, this can happen here, where 2 vibration analysts, 3 or even 4, can look on the same vibration spectrum and decide that the fault is different from one another. Theory versus practice. I will show you some example of how vibration signature actually look, while how theory predicted to look. The similarity between fault signature, as you can imagine, when faults start to manifest, vibration level goes high, and this could go high for a number of faults. So it makes it tricky for the classifier to distinguish between type of faults. It can distinguish that there is a fault, but what is the specific type, make it hard. So I don't have a lot of time, and I really want to dive deep into this specific section, but if you have any question related to the other type of challenges, so ask me later, or can ask me also by mail. We can even have another meeting. So when we started Ori, we built the first solution based on a handheld device, a piezoelectric sensor. We built a data acquisition system that connected to a mobile app, where any technician can come, record their machine, send the data to the cloud, and our algorithms then work on this data. And using this sensor, we were able to collect many data from many types of machine, and we managed to build good models for faults. Now, 3 years ago, even 4 years ago already, we built our first continuous monitoring system, which is also based on, as I said you before, accelerometers, which are vibration sensor. And when we try to apply the model for the fault detector that we build based on this sensor, although the machine are the same machine at the end of the day, we found out that there is a real degrade in performance, and I will show you that in the next slide. Now, the main reason for, probably won't surprise you, but the main reason for the degrading performance is that even if the sensor which is inside this sensing unit is the same like this sensor, at the end of the day, the mechanics which around it is different, and therefore the acoustic transfer function will be different. It will have different resonance response, the orientation might be different, the transfer function of the connection might be different, and it can change the vibration dramatically. Now we are in a process of building our second generation of continuous monitoring, which is this prototype unit, and also see the same issue, which we understand. So going into the main source of the issue and why, in contrast to the computer vision modeling, where it doesn't really matter with which camera you collected the data, as long as it's sent in some standard. Here, even if the sensors are in the same standards, you have three types of source that, or factors that can change the frequency response of the sensor. The first is the mounting, the stud and the glue response, and how you mount your sensor into the machine. The second is the structure and the material, the mechanics where the sensor is embedded into. And the third is the orientation. For example, if you use a single axis sensor, like you saw the handheld device, and you are taking a measurement, for example, in the horizontal direction, you are taking that from the horizontal section of the machine. While if you are using a triaxial sensor, you are measuring the horizontal direction from the top. Now, when measuring horizontal direction from the top, you also have the movement, the torsional movement, which is part of the horizontal direction. So you measure, in addition to the radial acceleration, you measure also a torsional acceleration. And this, of course, make the response quite differently. You can see here a theoretical simulation of the difference between radial acceleration to torsional acceleration, and you can see that the resonance of the torsional acceleration goes really low in the frequency. In addition, also, as I said before, the mounting also generate a difference in the frequency response. Like here, you can see the handheld device, the single axis sensor is being mounted on the machine using a magnet, where a magnet has a resonance below 10K, and the response started to elevate even after 1K, while the continuous monitoring system, which is connected with a stud and a glue, has a different frequency response. And you can see here some examples of comparing between the single axis sensor and the triaxial sensor, the continuous system to the handheld system. You can see the radial resonance at the higher frequency, and the lower resonance. You can see here that the triaxial sensor has elevated vibration at the lower frequency. Now, as you can imagine, if you take a snapshot of the triaxial sensor and embed it to a model that was trained on the single axis sensor, the result will not be that good. This is, by the way, another example for the difference. And this, here you can see the result, the precision recall curve of a model that was trained using the single axis sensor on 300K bearing recordings. And when you apply data of the new sensor to this classifier, the result degrades drastically. Question?
I'm curious how you're dealing with this problem right now.
Yeah, okay, I'll continue and jump to how we are tackling this. So one option is to start in doing calibration of the sensor, just calibrate the difference between the frequency response. Now that could be simple if the source was only, for example, the mechanics which the sensor is embedded in. But once once you add the stud and the glue, the orientation, and you add that this effect might be nonlinear, you will need to start building an experimental setup with multiple machines in order to calibrate this difference between a different scenario. What we decided to use is to map this difference using machine learning techniques. And what we understood that in contrast to traditional transfer learning method, where you have, for example, a classifier that can detect a specific object, and now you want to use it to detect a different object, so you usually can take the well-trained classifier, change the last layer, which is the fine-tuning features, and retrain it again with the new data. Here, the problem that we are trying to tackle is the same problem. For example, detect a bearing wear. And since it's the same problem, and the difference is the input data, is the difference between the sensor, we understood that we need to add a new layer on the top of the classifier and to freeze the classifier, because at the end of the day, once you calibrate the frequency response difference between the two sensors, then your well-trained classifier can perform well to detect, for example, the specific fault that you want. So what we did is we took the original classifier with the blue result trained on 300,000 bearing recording and freezed it, meaning freezed its weight, the weights of the neural network, add an additional layer on top of the neural net, and allowed during the training only to the weights of this layer to be adapted. And you can see that the result improved dramatically. Well, it didn't reach to the accuracy of the original classifier, but it improved really well compared to just plugging the data of the new sensor to the old classifier. Questions?
Yeah, so has your research and all this data you've collected, does that imply that it's the absolute magnitudes of these spectral data that really are connected to the faults, or is it the relative magnitude?
Can you repeat the question? I'm not sure.
So I'm thinking, like, if you have issues where, because if you could go back 1 or 2 slides to your spectrum graph, because it looks like, if I'm looking at this correctly, the peaks kind of appear in the same place. They're just of different magnitudes. Is that correct?
Yes, yes. It's related to the frequency will not change. The sensor, the accelerometers will not change the frequency. Of course, it will change the amplitude due to the acoustic transfer function.
So it's really that the data, or is there any opportunity to attempt to rescale these into some way that you wouldn't have such issues going between different mounting types or different types of sensors? Or is this something a little more inherent to it?
So if I understand the question, we did sort on the approach of doing the rescaling, but the rescaling is not a constant rescaling in frequency. It has a, for example, you can see here the difference change in frequency, and it might have also non-linear effect, which relates to the amplitude of the vibration. Therefore, we choose to go with a machine learning technique and let the classifier map between the frequency response differences.
Okay, thanks.
So this is the result, and this is what we are applying today in order to use the transfer learning approach. Now, we are now developing a new sensing technology, and it will be interesting to see how this approach can be adapted also for the new type of sensor, but we are still in the middle of development and research of that. Now, interesting thing, or what is important to do, is to do a relative comparison to a new classifier built only on the single, only on the new type of sensor using the 8,000 recording that we have. And you can see here that if you are building a totally new classifier from scratch, abandon the old classifier using only the limited data set that you have. So in the hierarchical, the result will be more or less comparable, and it makes sense in some way, but in the hierarchical, where there are more challenges in detecting the issue and the signature is not that pronounced, you can see here how the transfer learning approach outperform the baseline classifier, reaching to even 100% increase in accuracy. Well, I have time for this question, by the way. So one thing that was really interesting for us is if we can apply this mapping layer in order to learn differences between different type of sensor, not accelerometers which differ in the frequency response, but for example, a vibration sensor and a magnetic sensor, which we also use. Now, of course, for this to happen, you need to have some correlation in the physics of the sensor or the physics of the problem between the sensor in order for that to work. Now, what we knew is that any change in vibration or any change in the movement of the inner part of the electrical motor will be translated to a magnetic field changes due to the Faraday law principle. And vibration at the end of the day are a movement of the shafts and the inner part of the machine. So it was interesting to see if we can map the difference between a vibration sensor to magnetic sensor and try to build a classifier to detect bearing wear using only magnetic data. So we took the 8,000 magnetic recording that we had and applied it at the beginning to the original classifier using the single axis sensor. Of course, the results are very poor. No wonder here. And then we try to build a new classifier based only on the magnetic data and reach some not that good performance, because at the end of the day, to detect a bearing wear using magnetic data is not that successful. But what we saw that using the mapping approach, meaning using the original classifier that was built on vibration data and then letting the mapping layer to only be trained using the magnetic data, did yield better result than the baseline model, where you can see that at a bit higher recall, the results improve relative to the baseline model. Now, of course, again, using a magnetic data to analyze bearing wear is not that, or let's say in the beginning, we knew that it wouldn't succeed that much, but yet it was interesting to see how the mapping can work and correlate between different vibration sensor. Probably using a vibration to ultrasonic sensor will yield better results. Questions?
Are you trying to keep your solution non-intrusive? So not looking at doing anything with the electrical voltage or currents directly?
What?
So you're looking at the magnetics from it. Is there any reason you're not looking at measuring the current and the voltage going to the motor directly?
Yes, exactly. We don't want to be intrusive. And in order to have a wireless current solution, you need, first of all, an electrician to install it. You also need to open the controller box or the VFD box in order to plug your current into one of the phase, because if you measure the current on the three-phase cable wiring, so you will measure practically nothing. So you need to be on one of the phase, and magnetic installation is much more simpler. And at the end of the day, the magnetic and the current should be directly correlated. One downside of the magnetic is that the fields attenuate due to the shielding of the motor. So this is one downside, but at more than 90, I would say 98% of the data that we have, the magnetic fields show good SNR, good signal to noise, with values that are higher than, let's say, 100 milligauss and more. Well, I'm not sure that I have time for this section, but we'll be happy to answer any other.
Yeah, can I just ask a broader question? If we asked your customers what they thought the best features of your models were and the worst features, what would you say? What would they say?
Feature, you mean not the signal features, the feature of the solution?
That's what sorry, I should say, beyond all the marketing stuff, like what characteristics of the models are they happiest with, and what would they like to see you improve?
Well, I need to think of that, but Lior is with me. Lior, the VP of Engineering, probably he has a better answer.
Okay.
So, hi everybody. Nice to meet you. I'm trying to think about the question. I think that they will, in high level, like the fact that we keep safe their machines. There is a very little percentage of misses in our service, algorithm and human, and there is a relatively, not say very small, but relatively small false alarms. So they know they can sleep quietly at night when our system is there.
Lior, I thought of something.
Yeah. And they will want higher coverage. We're not still covering the entire production line. If they have, for example, robotic arms or machines like this, will not be covered. And in the business perspective, they have a secondary equipment. They will want us to cover also this, and we'll have it soon in the coming quarter.
I think, well, I thought about it a little bit, and I think that what customer really likes is that we take everything on us, from the installation and the service, and even the connectivity. If the customer is not willing to share, let's say, the wireless network due to some IT concern, we bring our own routers with cellular connectivity. So we're really taking everything on us. If we need to replace the hardware or a battery, it's on us. The service, everything is on us. And completing what Lior said, the customer can sleep at night knowing that we keep his machine safe.
Yeah, thanks.
So Ori, one of the things we've been trying to reinforce is how important data is. So if you do have some time, and for anyone that can hang on, could you take a few minutes and talk about the data section of the presentation?
Yeah, sure. So, by the way, just to know a bit your familiarity with vibration analysis. Do you guys more or less understand what is vibration analysis? Okay, so I'll try to share a bit background in order to dive deep into the data challenge. So in theory, vibration signature of the machine should be really simple. You have some known frequencies in the spectrum, like the RPM, the line frequencies, it's harmonic, the impeller frequency, and so on, and it's harmonic. And the fault signature also should be really simple. For example, 6 known faults like the 1X fault, misalignment, looseness, and balance, the bearing wear fault, which occupy around 35% of the faults. But in reality, this is how a spectrum look like. With lots of, beside of the peak that should be, lots of other peak, resonance due to the cavity of the machine, lots of resonance, by the way, multiple peaks related to the inner interaction between the component inside and how the acoustic wave travel to the surface of the machine. In addition to that, and this is more challenging, is that machine degradation, we want it to look like that, machine trends, like a cliff is a sudden change in a machine behavior. Trend is a more slow progressive change, or transient, which can happen if you change the operational parameter, operational speed of the machine, and you enter a resonance. But in reality, this is how trends of machine look like. This is how the vibration energy of machine look like, and see how many events you have in a machine life cycle. And I can start list them all, but it makes it really hard to achieve a solution with a really high accuracy, recall accuracy, while keeping the precision level, the false alarm level low enough in order not to tell the customer every hour, you have an issue, you have an issue. So this is one challenge that we are facing. And this is, we have a team of 11 data scientists that this is the main bread and butter, to try to improve the precision of the anomaly detection algorithm while not affecting the recall, keeping the recall at the same level. In addition to that, another two types of issue that we have in the data is that first, I said it multiple expert labeling. Usually when the false signature is not that pronounced, or where, let's say, the vibration analyst grew on a different methodology, they can analyze machine differently. You're probably familiar with the type of labeling from doctor that analyzing MRI scans, CT scans. So usually there will be the portion where the signature is really simple and all the experts will agree with one another, but there will always be those issue where experts won't agree, and when experts don't agree, the algorithm find it hard to learn how to, let's say, compensate on that. In addition to that, also faults sometimes have similar frequency, especially the 1x fault. 1x fault that occupy like the total free faults of 1x, 40% of all the faults. Those are unbalancing, mechanical looseness, and misalignment. They have similar signature. And when you calculate features that represent those signature, it makes it hard to train classifier to differentiate between them. Here you can see an example of an unbalanced detector that was unbalanced classifier that was trained using all the data excluding the rest of the 1x faults. So you can see the result, the precision recall curve, which is much better than the results while you are adding another type, the other type of 1x faults, for example. So we are facing a lot of data type issue like this. And again, our solution is like an insurance. And when you have a solution which is an insurance, you cannot degrade your algorithm performance. So this is a big challenge, to keep the level of recall accuracy while improving with time the level of precision. More or less, those are the challenges, the main challenges that we face today in our algorithm development. Well, if you have time, and I already started reviewing the data challenge, I can just share two more slides related to that. So one thing that we found really useful in improving the precision while keeping the recall level is that in our classifier, it's better to use several approach or several architecture of ML classifier, because each architecture, which is different, can learn different things, and the error can be different. And once you do, for example, a majority voting or logistic regression on the model's features, you are able to improve the performance. You can see here a precision recall curve of the bearing wear detector for time to danger modeling. For let's make it simple and say for severity levels. So when the severity is really high, this is the danger level. the model performance is not as good as when it's acceptable or the severity is in a monitor level, but yet you can see that each specific ML technology has its pros and cons and has a different level of accuracy, while when you are combining the 6th layer, you reach the highest accuracy. So this is one way we are solving the challenges that we have in keeping high recall and improving the precision. I also wanted to talk, I don't know if you're familiar, there was a paper by Google that was published, I think, a couple of years ago regarding wide and deep network. Did you heard about it? So wide and deep network are, you can say, simple MLP neural net, but the main advantage of them is that if you have some specific features which are really important for your classification, you can add them into the last layer of the neural net. And for example, what we found that using the mechanical features in a fully connected, so most of them has a similar weight in the decision, but the type of configuration and some operational parameter has higher weights in the decision. And for this, we are using a wide and deep network where we input the configurational parameter of the machine into the last layer of the neural net. And this what help us to enjoy all of the machine data set, the rotational machine data set, while still differentiate between the type of machine, for example, pumps, fan, compressors, chillers, and so on. Any question?
I know we're over time, but I'm curious how you do your confidence interval estimation. I don't know if you have a brief explanation of that.
How we do what?
Here, you said, do you have confidence interval estimation? So I'm curious how you do that estimation.
So the confidence is calibrating the score of the algorithm into the precision of the vibration analyst. And what the confidence means for us is the probability that the vibration analyst thinks that there is a fault. So after you are building your model and you have the confidence score, then you are going to the full data set and calibrate the scores of
I see.
Yeah.
Okay. How do you think about uncertainty of your predictions in general?
So it depends, and there are types of machine which there is almost no fluctuation in the accuracy, and the results are really robust, while certain machine like non-stationary machine that change their operational behavior even during the recording can be more tricky to analyze, and there you can have a higher fluctuation of your model results. But this will translate to low confidence, and the result, if there will be an anomaly or a fault, it will also be sent to a vibration analyst.
Okay.
Hello, I have a question. So it seems that you mainly use multi-layer perceptron-based model. Did you try tree-based model?
Yeah, of course. Here you can also see that in the stacking, we use random forest and gradient boosting. We are also using, those are classifier for faults. We are also using time series network like LSTM for the anomaly detection. We are not using only MLP classifiers.
I see.
For example, even for the electrical faults, because we don't have a lot of example, we're using a logistic regression. It works better than any other machine learning technique. So the data scientist, when he's building the model, he's trying various technologies and choosing what is more robust and provide the higher results, the best results.
I see. That makes sense. Thank you.
Thanks. Any other question? Okay, guys, so thank you very much for hosting me. It was a pleasure. You can get my email contact for any further questions that you might have, and I would love to interact and discuss with you about machine health issues.